In this section, we're going to be solving a series of equations, and what's different about these equations that the variable we're solving for is going to be an exponent, where that hasn't happened yet in the past. So looking at the homework, we're just going to go through a little sample problem from each one. So this is like from the first bit of the homework. I don't know what the problem number is. But anyway, a problem that looks like this. 2 minus 2x plus 1 is equal to 10. So the first homework problem from this section is something of this form where you have your variable and the exponent. There's only one variable, and then we want to solve for that. In the past, just when you're solving for x, you gotta get x on one side, everything else on the other side. And that still applies. So we want to start by getting x alone. The first thing we can do is just move this 1 over. So subtract the 1, subtract the 1. We'll have 2. 2 minus x is equal to 9. Okay, so now what we're going to do is we want to get x alone, but right now this x is an exponent, so it's kind of hard to do that. But then what we're going to do is we're going to look at this piece right here, this 2, this is called the base. So this is the exponent, this 2 minus x, and then this is the base. And so once we have it of this form where we just have, a base raised to an exponent equals a number, we're going to take the log of both sides. And if you remember in the last class, the log has a base. And so we can choose technically whatever base we want, but the base we want to choose is this number right here. So the base of this exponent. So what we're going to do now is take the log of this base, 2. So log base 2 of both sides of this equation. So 2 minus x equals log base 2 of 9. So here we took the log base 2 of the left, here's the left-hand side, and we took the log base 2 of the right, here's the right-hand side. And we chose 2 because 2 is this number right here, the base of this exponent. And now we're going to use some of the log rules that we had. Well, here's a power, this 2 minus x. And if you remember from the last class, if you have all those rules written out, if we have a power, we can just write the power in the front. So we can bring this 2 minus x and put it in the front. And then we have log base 2 of 2. Log base 2 of 9. So now we see x is not a power anymore. X is just, down here with everything else, so that's good. And another log rule we can use is, well, here you see we have log base 2 of 2. So the base and the inside are the same, so that just equals 1. So this is going to be 2 minus x times 1 is just equal to log base 2 of 9. And there's nothing we can do to simplify log base 2 of 9, but there's no reason why we can't just keep writing this. This is fine. So this times this, that's just 1. So let's just rewrite that. We have 2 minus x. Sorry, that times that is 2 minus x. 1 times this is just 2 minus x. Equals log base 2 of 9. And then what we could do now is subtract this 2 over to the right-hand side. Okay, now let's multiply both sides by a minus. So this is going to become plus over here. And we're going to multiply this side by a minus, so we'll have minus log base 2 of 9. And multiply this minus 2 by a minus, so it turns into plus 2. So this would be our answer. Okay, so now the second homework problem is going to be something of this form. So what's different about this is now we have two things that have exponents. There's an exponent here, that's the variable that we want, and here's an exponent here, again with that variable we want. So if you look, it's compared to the previous problem that we just did, they're two different things. This one only had one exponent, but here we have two exponents. So in this form, what we're going to want to do is put the exponent on both sides, and we're going to want to check for something first. We want to see, so we're going to look at both of our bases. So here's a 4, here's a 16. These are both of our bases. This is the base of this exponent, and this is the base of this whole exponent. We want to know is, can we write, for example, so here's 4. Can we write the other base, 16? Can we write that as 4 to some power? But very quickly we see that we can, since 4 squared is 16. We know that 16 is equal to 4 to the second power. So then what we're going to want to do is replace this 16 with this 4 to the second power. We want the bases to be the same. Sometimes that's not possible, but if it is possible, then we should do this technique. It makes it easier. So let's rewrite the left-hand side, 4 to the 3 minus x. And now 16, we said it was 4 squared, so it's going to be 4 squared to the x plus 1. So, okay, so now we replace the 16 with the 4 squared. So now what we can do is use the rules for exponents. And if we have an exponent raised to another exponent of this form, like this, we can just multiply these two exponents together. So the left-hand side still is 4 to the 3 minus x. And over here, we're going to have 4 to the 2 times x plus 1. Okay, so now we notice something here. We have 4 to something is equal to 4 to something. And there's a general rule that whenever we have, let's say something like a, raised to some function is equal b raised to a different, this needs to be an a. So we have a raised to, some things up here, b raised to some things up here, then we can just say that the exponents are equal to each other. That's what we have going on here. This f of x, that's like our 3 minus x. This g of x, this is like our 2 times x plus 1. And then the a's in this situation, these are like our 4's. So you see here we have a to the f of x, so 4 to the 3 minus x. And then a to the g of x, so again, 4 now to the 2 x plus 1. But using this rule over here, whenever we have the same base like this and 2 exponents and the things are equal to each other, we get to set the exponents equal to each other. So now what this tells us, using that rule, we can just say that 3 minus x is equal to 2 times x plus 1. X plus 1. Okay, so now what we have to do is solve this equation for x. So how we do that is, first we're going to distribute this 2, so 2x plus 2. Now just get x on the same side. Let's add this x over, subtract this 2 over. So we're going to have 1 is equal to 3x. And then what we can do is divide the 3 over. 1 over 3 is equal to x. Okay, and so that'll be how we take care of this problem. So let's move on to the next one. The next one's of the same form as the last one, but we're not going to be able to make the bases the same. So for this one, we have, let's do 11 to the x is equal to 12 to the 2x minus 1. So again, this looks just like the last problem where we have 2 bases with 2 exponents and we want to solve, there's an x here, there's an x here. And before we wanted to see, hey, can we make this base 11 or this base 12, can we make them the same? In this situation, we're not going to be able to make them the same. So then what we're going to want to do here now is we could choose either 11 or 12, and we're going to want to take the log of that base of both sides. Let's choose log base 12, just because that one has the more complicated exponent. Maybe that'll be that. Either way is going to be fine. That's just what I'm guessing is going to be easier. So let's take the log base 12 of both sides. Okay, so again, we chose that base. We do the same thing on both sides. Log base 12 of the left-hand side, log base 12 of the right-hand side. Now let's use those log rules. This x can come into the front. Now this 2x minus 1 can come into the front. Okay, log base 12 of 11, there's nothing we can do to simplify that. But over here we have log base 12 of 12. So that's just going to be 1. So let's rewrite everything. And again, just 1 times that is just itself, so. So the reason why we chose 12 here, why I thought it was going to be a good idea, is you see, if we didn't choose, if this was, say, log base 11 of 12, we wouldn't be able to simplify that. So we'd have this expression multiplied by this over here. I'm not going to do the steps out, but if you just are curious on your own to see why it's more important to choose the complicated exponent as your base of your log, you'll still get the right answer, but you'll see that the work's going to get way more messy if we chose log base 11 on both sides versus log base 12. But anyway, let's just keep continuing with this. So now we want to solve for x. So this thing right here, this log base 12 of 11, just there's really nothing special about that. That's just a number. So this is just like the same thing of saying instead of x times this, it's like x times 2 or something. So this log base 12 of 11, just we treat this as like a number. So we want to get the x on the same side. Let's start by subtracting this 2x over. So we have x log base 12 of 11 minus 2x is equal to minus 1. And just like before, so now we have the an x here and x here, so we could factor it out. Log base 12 of 11 minus 2 is equal to minus 1. And now what we can do is just divide this number to the other side. Okay, and so for this one, this is going to be our answer. Okay, so the last exponential equation is going to be something that looks like this. Okay, so whenever we have a problem that's of this form, you're going to have some variable to like maybe like 2x, and then another variable, the same thing, but only raised to the 1x and then nothing. So what we're going to want to do here is first like do this little substitution thing. So we're going to let u equal e to the x. And then I say if we squared both sides. So u squared is equal to e to the x squared. All we're doing here is squaring both sides. That's okay. But here we have a power to a power. So that just equals x times 2. So e to the 2x. So here we see if u is e to the x, then u squared is e to the 2x. So let's replace all of our e to the x's and e to the 2x's with u's and u squareds. So here's an e to the 2x. Let's write that as u squared minus 7. Here's an e to the x. Just write that as u. Then plus 10 is equal to 0. So now what we want to do first is solve this equation, which is easy. We've been solving this equation, I think, since like the first or second video. So we can solve this equation, just through factoring. We can have u minus 5, u minus 2. So then we get u is equal to 5, u is equal to 2. Okay, but then the problem tells us we want to find x, not find u. But finding u is just like part of the steps here. So after we find our u, we factor everything, solve for the u's. We're going to want to replace u with what we originally called it. We originally said this, u was e to the x. We just ignore this thing, u squared is equal to e to the 2x. And the reason we're ignoring it is because we don't see any u squareds down here. All we see is u's. So u is this, we're going to put an e to the x here and then an e to the x here. So e to the x is equal to 5, e to the x is equal to 2. So now we want to solve for x. Okay, so this is like the very, very first problem that we did from this section, where we just had an exponent, one variable, and then a number on the other side. And the way we solved that was once we got it into this form, we have to take the log of both sides of this base. So we're going to take the log base e of both sides, which is the same thing as the natural log. So we're going to take the natural log of e to the x, so that equals 5. And let's just do it simultaneously. So we have natural log of e to the x. Oops, sorry, this needs to be natural log of 5. And then natural log of 2. So we're taking the natural log of both sides, natural log of the left-hand side, natural log of the right-hand side. Here's natural log of the left-hand side, natural log of the right-hand side. So here, this exponent's going to go into the front. So x natural log of e is equal to natural log of 5. And let's do that same thing over here. X natural log of e is equal to natural log of 2. But remember, natural log, that means the base is e. So here we have a log with a base e and e on the inside. So again, whenever we see natural log of e, that just means 1. So this is x times 1. So really what we have is x is equal to natural log of 5. And same with over here, here's natural log of e, which is 1. So that means we have x is equal to natural log of 2. And so these are our two answers for this problem. Okay, so let's move on to something a little bit different now. So these were just exponential equations. So now we want to solve for equations, but the x is going to be in the inside of a log. So we'll do two different examples from this one. So the first one, say if we have log base 3 of 2 minus x plus 1, oh, there's a 6 in front, is equal to 13. So the way we want to solve this is, so we got some things over here, you know, the 6 and this 1, and then the log base 3 of 2 minus x. So the first thing we're going to want to do is get a log on one side, and then everything else we can onto the other side. So the first thing we can do is get this 1 and move it over to the right. So then we would have 6 log base 3 of 2 minus x is equal to 12. And then what we can do is take the 6 and divide it on both sides. Divide by 6, divide by 6. So log base 3, 2 minus x is equal to 2. So now we have a log alone on one side, and then just a number on the other side. And then what we're going to do, so there's a log rule that we didn't quite talk about. So say if we have something, you know, like, or let's just write the log rule out. If we have a raised to the log base a of x, this is just equal to x. So this is a power. So this is a raised to this power, log base a of x. So for example, like 7 raised to the log base 7 of 2x minus 1. This is just equal to 2x minus 1. Whenever you have this base and the base of the log the same and you're raising it, it's like this is your power, all you do is get the inside. So here our inside is 2x minus 1. So if we're doing 7 and we're raising it to the log base 7 of this piece, 2x minus 1, then we're just going to get 2x minus 1. So now we're going to want to take advantage of that rule here. So you see here we have a log base 3 on this side and then just something on the other side. In order to get rid of this log, we can use this rule over here, meaning we could take the base of this log, which is 3, and we're going to do 3 raised to the left-hand side is equal 3 raised to the right-hand side. Meaning we're going to do, so 3 raised to this power, log base 3, 2 minus x, is equal to 3 raised to this power. So again, we're doing 3 raised to the left is equal 3 raised to the right. And so now we can use this log rule over here. So here we have a 3, a log base 3, those cancel. So we just have 2 minus x. And over here we have 3 to the second power, that's just 9. Okay, so now if we solve for x, you know, you can add the x over, subtract the 9. You're going to get minus 7 is equal to x. And so before we can actually say this is our answer, we have to look back at the original problem. So there's something we have to take into consideration, and that's that whenever we have a log, so whatever's on the inside, let's just call it x, this x value has to be bigger than 0. So this is something we always need to keep in mind. So when we get our answers, so for example, x equals minus 7, we need to plug them back in. We don't necessarily need to see, the only thing we need to check is that if we plug this x value in to our original equation, are we going to get a negative on the inside of a log or a positive on the inside of the log? If it's positive, then it's going to be okay. But if we plug this answer in and we get a negative on the inside of the log, then we have to get rid of this answer. We'll say like there's no solution to this problem. So here's the problem. Let's just rewrite it again. 6 log base 3, 2 minus x plus 1 is equal to 13. If we were to plug x equals minus 7 in here, we're going to get 6 log base 3, 2 minus a minus 7 plus 1 is equal to 13. But what's important here is that this inside piece, 2 minus minus 7, that's just log base 3 of positive 9. So this 9 is bigger than 0, so that's okay. So we can accept this as an answer. If we were to plug this x value in and we were somehow to get a negative in here, then we couldn't accept the answer. There's only going to be one answer. Or in this case, there'd be no answers if this one made a negative on the inside. Okay, yeah, so for this one, we get a positive inside of the log, so this is going to be our answer, x equals minus 7. Okay, so let's move on to the next log equation. Okay, so our next one is going to be this, log of 2x minus 6 plus log base 2 of x is equal to 4. So this one's a tad bit different from the previous one, but we still want to do the same steps. We want to get one log on one side and then everything else on the other side. So in order to get one log, that means we're going to want to combine all of our logs together. And that was in the previous video. So we know that in this situation, if we have 2 logs adding, so log base a of x plus log base a of y, if we have something like this, well, that just means we can write one log symbol and multiply the insides. And that's what we have here. We have log base 2 of this plus log base 2 of this. So we're adding 2 logs. That means we can write one log symbol and then multiply the insides. X minus 6 times x, and that's going to be equal to 4. And now let's distribute this x on the inside. So we're going to have log base 2 of x squared minus 6x is equal to 4. So now this problem is exactly the same as the previous problem. We have a log on one side, a number on the other side. So what we're going to do is take the base of the log and raise it to both sides. Log base 2 of x squared minus 6 equals 2 to the 4. Okay, and now what we're going to do is, so here we have 2 to the log base 2. And then on the previous page, we saw whenever we have that rule, we can get rid of the logs and just have this inside piece. So we're going to have x squared minus 16x, and now 2 to the 4. So that's 2 times 2 times 2 times 2, which is going to be 16. Oh, sorry, I made a mistake here. This isn't 16x, that's just 6x. So this 2 log base 2 just gets rid of this, and all we have is x squared minus 6x. So x squared minus 6x is equal to 2 to the 4, which is 16. So now in order to solve this for x, let's move the 16 over. And so now what we can do here is factor this. So this is going to factor into x minus 8, x plus 2 is equal to 0. Again, minus 8 times 2 is 16. Minus 8 plus 2 is minus 6. And now we're going to solve this, so we're going to get x is equal to 8. X is equal to minus 2. So we have two answers here. So like before, we said we need to plug these answers in to make sure the insides of our log are going to be positive. So here's our original problem. Log base 2 x minus 6 plus log base 2 of x is equal to 4. So if we plug in 8, let's start with that one. See, if we plug in 8 here, on the inside of this log, we're going to get a 2, so that's going to be positive, so that's okay. And if we plug in 8 on this one, we'll just get an 8 on the inside, which is positive. So this 8's going to work, so we can accept that one as an answer. But let's try x equals minus 2. If we plug in minus 2 here, we're going to get minus 2 minus 6, which is a negative, so we can't have that. And again, if we plug in minus 2 here, we're going to get a negative. But we only need one negative for it to not work. Since we plug in minus 2 here, so you see we're going to get log base 2 minus 2 minus 6 plus the rest of the problem. But then this is going to give us log base 2 of minus 8 plus everything else. But we're not allowed to have that. So we have to get rid of this answer. So this one is not going to work. Only x equals 8 is going to be an answer for this problem. Okay, so the last problem from this section. So there's a formula that this next problem uses. It's a compound continuous interest. And the formula is P is equal to, A is equal to P e to the RT. And so A is going to be the amount after t time, and then P is the original amount. E is that number that is just, like the 2.71 goes on forever. And then R is going to be an interest rate. We'll just call it a rate. And then T is time. So for example, say if we have a problem. So we originally invest $1,000 with a rate of 16%. And we want to find the time, t, that it takes for the 1,000 to become 15,000. Okay, so here's a problem. So first, let's fill out all the variables that we have. It says we originally invest $1,000. So P means the original. So for this problem, that means P is equal to 1,000. And it says a rate of 16%. So R is the rate. That means R is going to equal to 0.16. We have to turn the percent sign into a decimal. So R is equal to 0.16. We want to find the time t, so we don't know t. And then we want it to become 15,000. So that's going to be the amount after time t. So our A is going to be 15,000. So now all we have to do is just fill in all these variables into here and then solve for the unknown. So our A, that's 15,000, equals P. Our P is 1,000. Then we have an E. Then we have our R, that's 0.16. And we don't know what T is. That's what we're solving for. So we're going to leave it in there. And that's the variable we're going to solve for. So this is just like the very first problem that we did from this section. So we can divide this 1,000 over. And if we divide the 1,000 over, we're going to get 15 is equal e to the 0.16t. And since this is an e here, we're going to take the natural log of both sides. So we'll have the natural log of 15, natural log of e to the 0.16t. And now we can use those log rules. This 0.16t is going to come into the front. So we'll have natural log of 15 is equal to 0.16t natural log of e. But this natural log, let's move up here. This natural log of e, remember that's the base of natural log is e, and the inside is e. So that means this is going to be 1. So we're going to have natural log of 15 is equal to 0.16t. And then the last step to solve for t is just divide by 0.16 on both sides. So we have natural log of 15 over 0.16 is equal to t. So this will be the time it takes for our money to turn into $15,000.